Okay, I think it's good. So hi everyone. Thanks a lot, Manki, for agreeing to speak here. So the title is on some difficult problem in string compactification and phenomenology. So the floor is yours, Manki. You have around 1 hour and a half. Thanks a lot again.
Thanks a lot. Thanks a lot for everyone for inviting me to give a talk. I'm not sure if I'll be able to fill up the whole 1.5 hour. But anyhow, if you have any questions or comments, or if you want to ask me for clarification, please interrupt and stop me anytime. So today I'll talk about some difficult problems in string compactification and phenomenology. And as a reminder, I'm not a string field theorist. I'm working on string phenomenology most of the time. So my understanding of string field theory is very naive and superficial. Therefore, most of the time I'll talk about string phenomenology and then what problems are giving us a very difficult time making progress. So, okay, let me start. So let me talk about what we want to do in string phenomenology. As you can see from the name, we string phenomenologists want to connect string theory to the real world. So that could mean many different things. Some people mean this thing, some people mean some other thing, but what I really want is to at least construct string vacuum that resemble our universe, and on top of that, I want to make some experimental predictions. And necessarily, if I talk about experimental predictions or the real world implications of string theory, I might be forced to talk about some entropics or the measure problem or the multiverses, which are not my favorite topics. So unless you really want me to talk about, I'll not really talk about those, but let's have a global overview, a broad picture that we want to connect string theory to the real world, our world. So then I need to talk about how we can connect string theory to the real world. Eventually, as I said, we want to make predictions that are practically testable within, say, 100 years. We cannot just vacuously claim that, okay, if we build a galaxy-sized collider, we can test string theory. That is not going to happen, and then I don't want to live long enough to see that happening. Of course, this is a very big problem in string theory, and there is a long way to go. And to really make experimentally viable predictions, one, we need to be very clever about which arena to look at. Two, probably we need to do a very precise computation using string theory, and both of which are out of reach at this point. So I'll be less ambitious, and then I'll set a very less ambitious goal, which is bringing me to this following question. So the question that I really want to ask nowadays, and many string phenomenologists want to understand, is the following: are there or are there not metastable vacuum of string theory that look like our universe at low energy? The qualifier low energy is really important here, because if you go to high enough energy, then everything doesn't look like 4D, it will look like 10D or some very stringy universe. So I want to remain at low energy, and then I want to ask whether or not there could be a string theory solution that looks like 4D, no SUSY, many particles, and positive CC, and etc., etc. As you can see, this question is not really a fancy question. Anyone can understand this question if they have heard about string theory. Despite the fact that this is such a simple and basic question, it has been really, really difficult to answer this question conclusively because of some technical difficulties. And because string field theory community is comprised of one of the most technically talented people, I want to talk about some problems that are really difficult which can be possibly solved by some string field theory folks here. Today, my computer is suffering from a lot of glitches. So when I'm talking about a vacuum that looks like our universe, what I'm really hoping to do is to find a vacuum that accommodates features that resemble our universe. So I'm not making any predictions. You can possibly say I'm trying to make post-prediction here. So let's discuss what features of our universe are required to even begin talking about semi-realistic vector of string theory. Yeah, let me fit those things. So one thing that I want to emphasize is that obviously in our daily life, we don't see stringy objects or stringy phenomena. If we have seen them already, we might have already come up with a theory of string theory like 100 years ago. But obviously, particles behave like point particles. This probably means that what we need to also require in our solution is that there is a TeV scale or some energy scale that we usually play with, and that must be much smaller than the energy scale of strings, let's say. Of course, when we're talking about string theory, there are a few more energy scales that must be introduced, but roughly speaking, we need a large separation between TeV and the string scale. And also, there is one more thing. We know that in our nature, there are only 4 fundamental forces, ENM and gravity. And we don't see any force mediated by scalar particles. But then the problem with string theory is that we see many massless scalar fields. And then if they are remaining massless, they can mediate some forces. And also they'll cause many instabilities. So when we're trying to find the solution of string theory, we should somehow remove moduli or give mass to moduli to stabilize them. The next point, maybe it should be quite obvious to the audience, is that we don't see any hints of supersymmetry at low energy. So when you're trying to find the solution to string theory, you also need to find a way to break SUSY in a reliable manner. The next point is somehow related to the second point, which is that the cosmological constant, at least to a good approximation, at present day, seems to be extremely small and positive. Of course, it can be some dynamical potential or rolling scalar, but to a good approximation, the dark energy looks like a cosmological constant, and it seems to be very small and positive. So when we're finding a solution to string theory, we need to also accommodate this feature. And then we should not forget that we are made of quarks and leptons, whose mass is generated by Higgs webs. So eventually, when we are sufficiently good at string theory, we also need to accommodate particle physics. And there could be many other things, such as the cosmological histories and the large-scale structure of the universes. But those are incorporating all those requirements at once is just too difficult. So I'll make my goal even more less ambitious by bringing down the criteria to just the first 3, and then I'll just focus on those first 3. And then even just realizing those first 3 requirements, large scale separation, no moduli, no SUSY, and small and positive CC will be extremely difficult to realize. So, okay, let me say again. So what I want to talk about in this talk is that, okay, we need to find string vector at low energy that look like that have 4 non-compact directions and large scale separation and small and positive CC. So I want to construct those vector. and there can be many different meanings associated to the word constructing string vector. So I want to explain what I mean by that. So if you're a string theorist who's doing string theory in mid-80s or mid-90s, you can possibly say that, okay, by constructing string vector, what I mean is to find a 2D CFT that is anomaly free and that has presumably four almost freely interacting bosonic fields that could possibly describe the non-compactifications, and the rest of the central charge should be solved up by some internal CFTs or some free fermions. This is a fine way to make progress, but there are several problems. The most fundamental problem is that, okay, the string perturbation theory or the finding to the CFT is done by perturbation theory. So even if you find the 2D CFT on the worldsheet, say, sphere, you need to include the effects of torus or annuli or genus 2 surfaces to guarantee that your solution is really a solution. Two, this is a rather technical point. We don't really know how to find strongly interacting CFTs at central charge, say 9 or 15. So although this is a fine view to take, it is almost impossible to practically execute this protocol. The other point of view one could take is that, okay, I'm a string field theorist, and string field theory is a well-defined theory or well-defined description of string theory, and what I can do to find the vacuum is to solve the solutions, find the solutions to equations of motion of string field theory. But of course, we know that although this is also a fine protocol, it is practically almost impossible to execute. And more ambitious person to say, okay, we need to find a non-perturbative description, a fully non-perturbative description of string theory, I don't know what it is, and then find the solution to the equations of motion of that non-perturbative formulation. Of course, we don't even know what the non-perturbative formulation is, and it's not really clear when we'll have any access to finding solutions to the equations of motion of such a non-perturbative description of string theory. So this looks like a very difficult problem. And to make progress, I'll make some compromise. The compromise is by making a conjecture. Let me explain what conjecture that I use. So this will be a very practical but a mundane way. So what I'll assume is the following. A vacuum solution to the equations of motion of low energy vector theory of string theory, say that if you have some low energy SUSY, this low energy vector theory might be some supergravity in 4D. And I'll assume that the equations of motion to that low energy supergravity theory corresponds to a vacuum of string theory. This is a very reasonable thing to assume because, for one, the vacuum structure is an inherently low energy phenomenon. So anything about low energy phenomenon should be describable by low energy vector theory. Furthermore, we know that when we have a string worldsheet description, the string worldsheet becomes a CFT when the beta function of string worldsheet theory is vanishing, and then the beta function of string worldsheet QFT corresponds to the equations of motion derived from the low energy supergravity. So this is an assumption, but I judge this assumption to be very reasonable and well-founded. But this is still a conjecture, and some people object to this idea. So I'll have to make it clear. The reason why I'm taking this point of view or this approach is because this is a very practical way forward. Unlike finding CFTs or unlike finding solutions to the equations of motion of string field theory, finding solutions to the equations of motion of supergravity theory is much more easy. So, of course, to really make sure that you're doing the good and the right thing, you need to derive the low energy supergravity action from string theory. You cannot just propose some random supergravity action and then solve the equations of motion and claim the victory. That's not the way to go. And this part, where deriving the low energy supergravity effective action from string theory, will be the hardest part in this program. So let me recap. The goal has changed from the grandiose goal to a much more practical and mundane goal. Let me summarize them. First, we need to compute the low energy effective action derived from string theory with a desired precision. Two, we need to find vacuum solutions using the low energy effective action. Three, at a point at the vacuum, we need to ensure that the unknown corrections to the low energy effective theory is small enough compared to the leading orders that we have computed so that our vacuum solution is well valid. Of course, this cannot be an exact solution, so this will probably give us a very good guide to where to look at to find the CFT description or solutions to the string field theory. So when people are trying to follow this program, the most common approach that people take is as follows. First, you can try to hide some 6 dimensions away by compactifying string theory on some manifolds. There are many different choices of manifolds. You can compactify your string theory on T6, like 6-dimensional torus, or T2 times K3, where K3 is the unique 4-dimensional Calabi-Yau, or you can compactify your string theory on a Calabi-Yau threefold, or Calabi-Yau rentifolds, or some hyperbolic manifolds. But in this talk, we'll focus on heterotic string theory compactified on Calabi-Yau threefolds, or type 2 string theory compactified on an rentifold of a Calabi-Yau threefold. The reason why I'm doing this is very simple. If you compactify string theory on, say, torus, then you have too much supersymmetry. And if you have too much supersymmetry, it is really difficult to stabilize moduli because there is too much supersymmetry. And then the effective theory that you'll get out is awfully unrealistic. And furthermore, it's really difficult to achieve a scale separation. We have a very good understanding that if you have too much SUSY, then there is almost always no scale separation. On the other hand, you can go the other extreme. If you take string theory compactified on hyperbolic manifolds, let's say, then now what you're finding is that, okay, the SUSY is awfully broken at high energy, so we don't really have a very good computational control. So we need to find somewhere in between the hyperbolic manifolds and some toroidal compactifications. And the RANA that I'll choose is a Calabi-Yau threefolds in heterotech or Calabi-Yau rentifold in type 2. The reason being is that the low energy effective theory of such a compactification is 4D n equals 1 supergravity. And the 4D n equals 1 supergravity has a minimal SUSY, which means that I have some control of the computation, and the low energy effective theory could be semi-realistic at least. Of course, as I told you, I want to obtain non-supersymmetric. I'm curious about non-supersymmetric solutions, so I cannot just keep the supersymmetry forever. So eventually, I'll have to break supersymmetry softly at low energy, but that will be discussed later. Then, as I said, what you will have to do is now to compute the effective action. So in principle, what one can do is the following. Say that you are really good at string perturbation theory. Then what you can do is to compute n-point functions up to arbitrary genus. Say that you're computing 3-point function on sphere, on disk, on torus, on annulus, and then you can keep going. And then the right thing to do here is to write down the low energy effective action of supergravity that matches the scattering amplitude at low energy. And those will be represented by some kinds of Feynman diagrams. The crucial point that I want to really emphasize here is that because we're not really good at string theory, most of the time the computation will be done in a fixed background. By the fixed background, what I mean is that there will be no RR flux, there will be no NSNS flux, and then the RR tadpole will be saturated by space-time filling d-branes. So the best we can do practically is to saturate the RR tadpole using d-brane and compute the fluctuation of the RR flux or NSNS flux around that background. So one thing that we could possibly miss is the effect that is only generated at strong flux limit or when the flux is not dilute. But anyhow, I want to really emphasize that when we're doing this computation, you need to compute the modules of the effective action, for example, dBi actions, and how the dBi action is coupling to the RR flux or NSNS flux, or how the bulk fluxes are coupled to some closed string moduli. And then you need to understand how to carry that information over when you're changing your configuration to a non-trivial flux configuration. The reason being is that because we cannot easily compute string perturbation theory or string scattering amplitudes in a non-trivial flux background, and this will be an important point later in this talk. Okay, so yeah, and of course, this is a nice story, but in principle, but in practice, it is really difficult to carry out because we're not really good at computing string loop corrections in general. And then furthermore, when you have some Calabi-Yau or interval compactification, string loop corrections or higher loop computations in string perturbation theory will require the spectrum of Calabi-Yau CFT, let's say. And we don't even know how to construct Calabi-Yau CFTs from the first principle. So if I start asking questions that require to find information about the Calabi-Yau CFT spectrum, then there is almost no way that we're going to make a reliable or reasonable progress. So this fact that we don't know much about the loop corrections will also be a very important point later on. And this is a parenthetical remark, which is that the vacuum structure for the n equals 1 supergravity is determined by three quantities. One, the Keller potential, which is a real function of holomorphic moduli. Superpotential, which is a holomorphic function of moduli, and the gauge kinetic time, which is also a holomorphic function of moduli in the Wilsonian picture. The Keller potential here will determine the kinetic time of moduli fields, and superpotential will generate some energy barrier for the moduli fields, and gauge kinetic time, as the name says, will determine the gauge coupling strength. And now, this is a highly non-trivial step. When you don't have any non-trivial fluxes, like NSNS or RR fluxes, then there is absolutely no potential for moduli, at least perturbatively. Of course, the potential can be generated non-perturbatively via some d-instantaneous effects, but perturbatively, the moduli space is flat. So what you need to do is to actually turn on some NSNS and RR fluxes, and then taking into account the tadpole cancellation, and then include some number of d-branes to ensure the tadpole cancellation. And you need to compute the effective action using the previously mentioned modules. So a crucial data that we need to use here is the potential, which can be roughly written as sum of F-term potential and the D-term potential and the supersymmetry breaking source. So of course, supersymmetry breaking can be coming from the F-term potential or the D-term potential, but I just pulled it out here. And the F-term potential is given by this formula. there is e to the k, where k is the Keller potential, and then the standard form is that there is dw squared, where d is the covariant derivative in the moduli space, and there is 3w squared. And now the rule of the game is that you minimize the potential and you find the solution to the equations of motion where the potential is minimized, and that will be an isolated supersymmetric vacuum. And of course, eventually you'll want to also add some supersymmetric breaking sources, and that's the whole another story, but let's for a moment focus on the supersymmetric vacuum. Then at the vacuum, you need to what you need to ensure is that the corrections to the effective theories are small. For example, there could be corrections to the superpotential, or there could be corrections to the Keller potential. And then you need to make sure that those corrections are small so that our approximation is valid. So basically, this is the scheme. Then you can ask, okay, this looks doable and straightforward. So what is all the fuss about, and why are people not making good progress here? So to illustrate the point, let me first give an overview of the terms that we know how to compute it and of the terms that we do not know how to compute. So as I said earlier, the Keller potential, which determines the F-term potential and the kinetic term for moduli fields or low energy fields, is a real function of moduli. Of course, that can also depend on fluxes and topology of the compact directions and D-brane configurations. Now what I'm going to do is to expand the Keller potential using string loop parameter, like e to the minus 2 phi, where phi is a dilaton, and then I can pull out the tree-level contribution, and then next the leading order, I have one contribution, and then I'll have genus tree half contribution, and so on. What I want to tell you is that we know really well how to compute the tree-level Keller potential in the absence of the flux. The reason why we can compute such a thing very precisely is because there is amazing tool on mirror symmetry and SQLT that basically fully determines the kinetic term of moduli fields at the level of N2 supergravity. And then if you're taking an rent-fold of an N2 supergravity to break SUSY into N1, then we can basically take all of the structures of N2 supergravity. And this is why, in the absence of the flux, we know very well how to compute the tree-level Keller potential. Of course, this carries over to higher loop corrections to the Keller potential that are coming from closed strings. And the problem is that when there is a non-trivial flux, we don't really have such a good tool to compute the Keller potential. And even at tree level, we don't know almost anything about the Keller potential. If you have been following the debates about the KKLT, anti-D3-brane SUSY breaking, and the swampland debate, etc., 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 much of the debate is rooted in the fact that we don't even know how to compute the tree-level Keller potential precisely in the presence of the fluxes. And that's why many people have to make some ansatz and guesses, and then they are the source of the debates. And in the absence of fluxes, there have been some progress. For example, in toroidal rentifolds, the one-loop correction to the Keller potential was computed in details. The reason why it was possible to compute such a one-loop correction to the Keller potential is purely because in the toroidal compactifications, you know the full spectrum of open strings and closed strings. And typically when you write down, if you're thinking naively, when you want to compute the Keller potential, you'll need this string spectrum. That's why the only computation that was carried out was in the toroidal rentifolds. But recently I started making some progress to compute the Wonder correction to the Keller potential for Calabi Fourier intervals. Yeah, I wish I can write something down because I wanted to write some formulas here. But the catch here is that the finding of this paper is that some parts of the Keller potential are computed by the protected quantities of your worldsheet CFT. So even though naively one might think that you need to know the entire spectrum in gory detail, in fact, the string theory is not really harsh enough to us so that we can use some topologically protected sector of string theory. Of course, this is just a partial progress, and there is a long way to go to complete the computation of the Keller potential at one node, even in the absence of the fluxes. And that brings me to an overview that we know almost nothing about. The Keller potential correction in the presence of the flux, or one or higher corrections to the Keller potential, even in the absence of the flux. So that was about the Keller potential. Now let me talk about the superpotential. The situation for the superpotential is a little bit different because the superpotential itself is a holomorphic object, and then the fact that it is a holomorphic object makes the computation much easier than the Keller potential because we can use supersymmetry and holomorphicity and many other tools, analytic tools. For example, in type 2B string theory, the tree-level superpotential is given by the famous Gucko-Papa-Witten superpotential, where F is the Ramon-Ramon three-form flux, tau is the axiodilaton, H is NS-NS three-form flux, and omega z is a holomorphic three-form defined on a Calabi three-form. And then this tree-level superpotential, we know really well how to compute this up to arbitrary precision. It's just a computational problem. The nice thing is that due to the holomorphy and some axionic shift symmetry, we know that the superpotential is perturbatively exact, meaning that the tree-level superpotential is all there is perturbatively. Of course, it doesn't mean that there is no non-perturbative corrections to the superpotential, and there are in fact such corrections generated by some Euclidean D branes or NS5 branes wrapped on some cycles. Of course, in type 2B, NS5 branes cannot generate a superpotential term, but in type 2B, Euclidean D3 or Euclidean D-1 instantons can generate the terms in the superpotential. So that is what I wrote here, where gamma is some cycle in Calabi-Yau, A is the one prefactor of the non-perturbative superpotential, and T gamma is the tension of a Euclidean D brane wrapped on some cycle gamma. And we don't really know much about the non-perturbative superpotential. So you might have heard about the recent series of work done by Ashok and Sergey and Bogdan, and many collaborators of Ashok, and including also a work done by Harvard group, that you can actually determine the non-perturbative corrections to the effective theory has been really difficult quantities to compute. But somehow, in the past, people were able to figure those non-perturbative corrections out using some clever combination of S-duality, mirror symmetry, and various other SUSY algebra. And then those confirmations, those predictions were confirmed by string field theory computation. In the case of superpotential, the non-perturbative corrections to the superpotential, we're not in a luxurious position to actually predict or guess the one prefactor here. The reason being is that we're playing with n equals 1 supersymmetry in 4D. There is just simply not enough supersymmetry, and the duality in n equals 1 in 4D is not strong enough so that even if we are combining those two, it's really difficult to really know much more about the actual behavior of the one prefactor here. So what I'm alluding to is that, okay, because we don't have a clever tool to compute such a one prefactor A gamma, we need to compute them explicitly directly using string logic CFT. But we know that computing one prefactor of the non-predictive correction to the effective theory is really difficult. And this is primarily due to the IR divergence, due to the zero modes, and lack of our understanding of open string spectrum. Sorry. Despite the difficulty, there was a recent progress by myself, Ashok, Atakan, and Bogdan and Sergey in this paper, using string field theory techniques, following the Ashok's prescription to regulate the IR divergence. We fixed the IR ambiguity of the non-predictive superpotential corrections. But still, string field theory will not really tell you how you can fully compute the non-predictive superpotential, because after fixing the IR ambiguity, what you are having is that, okay, we need some open string spectrum to actually evaluate it. But then also recently, in one of my recent papers, it was realized that the open string spectrum was related to the one partition function of open topological string theory, which is much more easy to compute. So at least in the fluxless vacuum, in a fluxless scenario, I think it is safe to claim that we now know how to compute the one prefactor of the non-predictive superpotential. But as I emphasized, to stabilize moduli, we need to turn on fluxes, but the computation was done in a fluxless case. So although it was a reasonable thing to do for the first step, I think we need to extend our computations to a non-trivial flux cases. And computing the non-predictive corrections to the superpotential will be very important, because they will also mediate exponentially suppressed UCAR couplings for particle physics sectors, although I will not talk about this in much detail. So that brings me to the Dine-Seiberg problem. The reason why I want to talk about the Dine-Seiberg problem is as follows. You can possibly say the following thing. Okay, say that we have an infinitely strong regime to compute string loop corrections. So what I told you is that at the present moment, we don't really know how to compute the string loop corrections to the effective theory very well, because we're not really good at string theory and Clavier CFTs and all. Then you can possibly worry that, okay, then if you really want to find string vacuum with stabilized moduli and all the requirements that I spoke of in the beginning, you might want to reside in a regime of the moduli space where string coupling is small and the compactification volume, Einstein frame volume, is large, so that the computation is under control and we don't have to do high order computations in string theory. The problem is that when string coupling is small and Einstein frame volume is large, we more or less know that the potential will always approach zero. The potential can approach zero from above or from below, but no matter what, it will always go to zero. So what you need to do is that, okay, fine, then probably I need to compute one more correction, like one loop correction. But then oftentimes what you'll find is that in a point around the point in the moduli space where the loop counting parameters are small, just computing one or two loop corrections to the effective action may not be sufficient, because it is not really enough to deflect the behavior. then eventually what one may conclude is that, okay, then we may need to go to 3 order, 3 loop, 4 loop, 5 loop, or say 100 loop. And then we need to go deep into the moduli space where the behavior of the potential can eventually change. And even if the behavior is not changing, one thing that I really want to know is to really see that there is a minimum. And then because all we can do is happening here, and then even if there is a deflected minimum or some minimum without any deflected behavior, because if you want to reach here in the moduli space, you need to compute many, many corrections to the effective action. Probably you will never get there because those are probably in strongly coupling regime. And this is the so-called Dine-Seiberg problem. So this is a big problem that we cannot easily avoid in string theory because string perturbation theory, string worldsheet CFT is defined perturbatively. So to this problem, you can have several reactions. Of course, there'll be always some brave people who will say, okay, I don't care. Let's compute G string and alpha prime corrections to higher orders until we find vacuum. This is something that we need to eventually do in order to explore all kinds of possible vacuum solutions of string theory. But I don't know how long it's going to take, and I'm not really brave enough to actually carry out this program at this point. Some people might say, okay, this is never going to work. I'm going to give up. So those are two primary, those are two reasonable reactions, but there could be some other reaction too, which is a point of view taken by Kachur, College, Linda, and Trivedi in 2003, and many variants thereof. So what they say is that, okay, this looks like a very difficult problem, and let's find a way to actually stabilize the moduli by avoiding this problem by looking at looking cleverly at a very special arena in string theory. And this is the whole point of KKLT. And then because I'm talking about moduli stabilization, I kind of have to talk about KKLT. So I'll give you a one-slide summary of KKLT. The core ideas of the KKLT are as following. Although it is not proven, it is likely, or it makes sense to assume or think that the large Einstein frame volume and small string coupling will suppress string loop corrections because those are giving us the string loop parameter in 4D n equals 1. The other idea is that computing superpotential with exponential precision is much more easier than computing the Keller potential precisely. So if you identify an arena where you can live off of a very precise, almost exact superpotential, and if you can neglect some higher loop corrections to the Keller potential in a reasonable manner, then possibly there is a way to make progress in a practical manner. Although this is going to be a very special case in the whole wide of possible scenarios, because there could be some possibilities to stabilize moduli by computing higher loop corrections to Keller potential. But because those are out of reach at this point, I really think this is one of the best ways to make progress. And the KKLT is a scenario to stabilize moduli in type 2B, and I'll explain the reason why they specifically chose type 2B string theory. So as I said, I'll look at type 2B string theory on a Calabi-Yau interval. And there are 3 types of closed string moduli. One is the complex structure modulus that basically describes the shape of the Calabi-Yau. And there is the Keller moduli, which describes the Einstein frame divisor volume. By divisor, I mean complex codimension 1 surface in a Calabi-Yau threefold. and tau, which is a complexified 1/G string. And as I mentioned earlier, the tree-level Kähler potential in the absence of the flux can be almost exactly computed using mirror symmetry, which is given by this form. And now we can write the superpotential again, where the tree-level superpotential is given by the flux superpotential, and the non-perturbative superpotential is given by the d-instanton corrections. Then what KKLT said is that, okay, you can stabilize Kähler complex structure moduli and the axial dilaton using tree-level flux superpotential by solving the F-term equation here. Then after solving the F-term equation, you will have some vacuum expectation value of the tree-level superpotential. Then in a rather simple manner, one can one can write down the F-term equation for the Kähler moduli, which is written as follows. And then the solution of the F-term equation to the Kähler moduli is roughly written as following. So T is the complexified Einstein frame divisor volume. So what it means that if T is large, then Einstein frame volume is large, hence probably the corrections are suppressed. And this solution can be solved at large Einstein frame volume if W0, if the value of W0 is extremely small, because you can rewrite this equation in terms of T is roughly the same as minus log of W0. So if you can really find small W0 and large Einstein frame volume, maybe, although it is a conjecture at this point, maybe the tree-level Kähler potential is enough. And then you can break SUSY using some anti-D branes or whatnot, but this is an extra step. So, and I want to really emphasize again, as you might have been picking it up, I really want to stress that the standard assumption made by KKLT that small G string and large Einstein frame volume will suppress the string lobe corrections to the Kähler potential, although it is a very reasonable assumption to make, has not been confirmed. And then we also do not know how big they are or how small they are, because we have never really explicitly computed those corrections in Calabi-Yau compactifications. And this is basically one of the major sources of debates and discomforting feeling for many people, especially in the swampland community. So what I say is that without computing those corrections to the Kähler potential in particular, it might be impossible to reach a consensus among the community within string theory community or string pheno community more narrowly. Then it might be almost impossible to really claim that, okay, we have a way to connect string theory to the real world. So I think this is one of the most important problems in string phenomenology, and then perhaps even in string theory. Because if we cannot connect string theory to the real world, then what are we doing here? We're doing some mental gymnastics or mathematics, right? So this finally brings me to the practical open problems in string phenomenology. The first thing is, can we compute string loop corrections to the Kähler potential? This is mostly CFD computation. It's not really a string field theory computation, but because string field theory community is comprised of technically gifted people, I think this is a problem that might be accessible to string field theory folks here. And then, of course, the second problem: can we compute the flux, the corrections from the non-trivial fluxes to the Kähler potential, even at tree level? This is not just a simple CFD computation, because when we include non-trivial fluxes to the worldsheet theory, the worldsheet theory is no longer a CFT unless we're at a vacuum, but the finding a vacuum is again a difficult problem. So we don't really expect to see the solution to that. But anyhow, when you deform your CFT using the fluxes, then your theory is no longer a CFT, so presumably you will have to use string field theory. Then the question is, can we compute the corrections to the Keller potential from fluxes using string field theory? And of course, the other important problem is that, as you might have seen, or as you might have realized, is that in the living paradigms or living scenarios for moduli stabilizations, the non-productive superpotential terms play significant roles. And then without computing the one prefect of the non-productive superpotential precisely, we might never be able to really say precisely at which point the moduli is stabilized. So the other question that I want to raise is that, can we really compute the one prefect of the non-productive superpotential generated by the instantons in non-trivial flux configurations? And this is really important because we need fluxes to stabilize moduli. And the rest of the final question is, can we use string field theory to understand the soft SUSY breaking? The reason why this is a technical problem is that with the present tools that we have in string theory or string worldsheet CFT, the best we can do is to guess what the SUSY breaking effect is. But it is really, really, really difficult to precisely compute the supersymmetry breaking effect, especially the supersymmetry breaking contribution to the potential. So I think this is possibly a question that can be probably addressed by string field theory. So I think this is a good problem for some string field theory people as well. Of course, there could be more ambitious goal. The first ambitious goal is that, can we or can we not prove that solutions to the equations of motion of low energy supergravity, let's say, is indeed equivalent to a string vacuum? I told you that this is an assumption that I'm going to use, and many people use in string phenomenology. Although it is a reasonable one, this remains a conjecture. And if one can prove this statement, then that can improve our understanding of string vacua significantly. And also, if there is anything that string field theory is really good at, is when the worldsheet theory is not a CFT. So that brings me to a question: can we understand time-dependent solution of string theory, such as inflation or reheating or early universal cosmology, using string field theory? This will be difficult, but I think this will be very fruitful if one can do this. And of course, this also brings me to a question: can we find solutions to string field theory directly? Those three problems are really big. So I don't know when we can have a handle on those, but I think it might be useful to say them out loud. Okay, this is pretty much it. If you want to ask me about how one can actually compute the Keller potential, I can also talk about it, but this is more of a technicality. So unless anyone has any question, I'll just stop here.
Okay, thanks a lot, Manki, for the talk. So I think we can, as usual, like, take a few questions with recordings if anyone has, and I will shut down recording and we can ask more questions to Manki offline. So does anyone has a question for Manki? Okay, seems no, so I will stop recording.
Yep.